Now that we have an idea of strong acids, weak acids, and their equilibrium calculations, we can add another layer of information, folks, and that is polyprotic acids. So poly is going to mean many, and protic means proton. This means you're going to have acids that have more than one ionizable proton, okay, folks? And so if we're looking at something like H2SO3 Jean Grey, we see that we have two hydrogens here. And so H2SO3 Jean Grey is going to represent a diprotic acid. So di means two, and then protic means protons. I mean, it has the ability to ionize or donate two of these protons here. You also see triprotic, like we see in this table down here for H3PO4, for example. And of course, a lot of our weak acids are monoprotic, right, which is the examples we saw beforehand. So this is adding another layer of information because we do have strong polyprotic acids and weak polyprotic acids. A couple of strong polyprotic acids that we saw will be like sulfuric acid, for example. And guess what? Every single ionizable proton that gets to be donated has its own Ka value and will have a specific ionization step in a reaction. So for H2SO3 Jean Grey, that's what we're going to start off with here. We're going to take that weak acid and mix it with water, just like every other way that we create our weak acid reactions, right? That's going to produce H3O plus and our new, right, conjugate base. And this conjugate base is a little bit different because it still has that proton attached to it. It has the ability to now give up another proton. So when H2SO3 Jean Grey has the ability to give up that proton, she is then going to form HSO3 minus Phoenix. If we know anything about Phoenix, Phoenix is very powerful. So the fact that Jean Grey is able to get to this point means that you have a Ka value that's actually very strong, usually stronger than Ka2 values, or if you have 3 protons and Ka3 values, Ka1 is always going to be the value that's way larger. And so when you're looking at Ka values, our Ka1 is larger, then we have our Ka2, then we have, like if you have Ka3, for example, that will be smaller and smaller and smaller. And we can see that here. When you're taking our first proton that's donated, our Ka value is 1.4 times 10 to the negative 2. By the time H3SO minus Phoenix is going to donate its last proton, our Ka value is 6.5 times 10 to the negative 8, much smaller. Now, what do we know about HSO3 minus Phoenix? We know they still have an ionizable proton. And so if we were to get our second step to show that this proton is being donated, this proton is going to be attached to water. You're going to form H3O plus, and now you're going to form your conjugate base, SO3 2 minus, which is the sulfite ion. Okay, folks? Now let's think about this. If bisulfate Phoenix gives up its last proton, then we're now going to have SO3 2 minus Phoenix, which is super uncontrollable. If you know anything about Jean Grey, the goal is we don't want to bother her too much because we don't want her to get to the Phoenix level, right? Now, if she gets to the HSO3 minus Phoenix level, that's fine. But any further, then of course she can implode and start to destroy the entire universe. But we don't want that. So what ends up happening and what we see in all of our normal equilibrium reactions is that we assume that virtually all the H3O plus that is going to disassociate is coming from that first proton release. So the only Ka value we focus on is the Ka1 value. That means the Ka2 values, if you have another or third ionizable proton like the Ka3 value, would not matter when it comes to our equilibrium concentration. This doesn't mean it doesn't matter in general. It just means that for our equilibrium concentration or calculations as well, we're going to focus on the Ka1 value. Okay? Now, if you have to go and figure out Ka2, you would still use the Ka2 expression, and you can go ahead and calculate and solve just like anything else. When we're talking about rise tables, we're focused on our Ka1 value mainly. And another big reason why is that it's going to be way more difficult for a proton to leave a charged molecule than something that's neutral. So this HSO3 minus is going to be very difficult to get rid of that proton here to form SO3 2 minus, which is another reason why the K value is quite small. Whereas it's way easier to remove a proton from something that's neutral. So again, focus only on the Ka1 value, and you can ignore the rest when it comes to our Rice table calculation. And we're back at the Avengers compound for an example. So now we see we have ascorbic acid here, which is going to be H2C6H6O6. And so as you can see, we definitely have those two ionizable protons here. And so we can rewrite it as a simplified version as H2ASC right here. So we're going to have our H2ASC. We're going to go ahead and mix that with water, and we're going to produce H3O plus, and of course, HASC minus. Then we're going to take our HASC minus. We're going to then mix that with water and get rid of our next proton, just so we can show where all these Ka values are. Remember, we're in polyprotic land now, so we have to make sure we have all of our steps. We're still going to have H3O plus here, and now we're going to simply have ASC minus. Let's go ahead and continue to read. They gave us, and they told us it was diprotic. That's the reason why it's easy for me to have these two steps here. And then they gave us the Ka values. So they said Ka1 is equal to 1.0 times 10 to the negative 5, and Ka2 is equal to 5 times 10 to the negative 12. So of course, Ka1 is much larger. That's the one we're going to focus on when it comes time for our rice table. So what did I essentially do? We've been doing a couple of these problems already, right? So all I did was go ahead and write my balanced chemical equations and write down my Ka values. But what else do I need to do? I need to go ahead and write out my Ka expressions as well, because that's just going to make sure that I have everything in mind for Ka1 and Ka2. So Ka1 is going to be HASC minus times the H3O plus, of course, divided by H2ASC. And then our Ka2 value is going to equal our ASC minus, or our conjugate base, times H3O plus divided by HASC minus, okay? So let's go ahead and continue reading. So we have H2ASC, known as vitamin C, is diprotic acid. They gave us our Ka values, and it's found in citrus fruit. They want us to calculate the equilibrium concentration of HASC minus and the equilibrium concentration of ASC2 minus, okay? Got my 2 here. And then they gave them the pH of 0.050 molar H2ASC. Okay, so they give us the initial amount of our H2ASC. And we're asked to get the equilibrium amounts of this particular species and this particular species. Okay, folks, they did also give us, and they want us to also get the pH too. So let's check. We know we have to focus on our first Ka value for our rice table, right? So if we get our Ka value, we effectively are going to get the concentration of HASC minus. So then we'll have this concentration. We can get this concentration. Let me make sure I have a different color. We already have our Ka1 value, and we can use that in our rice table to help us get all these different concentrations here, right? Once we have all these different concentrations, they want us to basically, we'll have this amount. Then they want us to get the pH. We can use H3O plus to get the pH there. Then they want us to get the ASC2 minus amount, and that is from our Ka2. So we have our Ka2 value. We would already have this value. We would already have that value. All we need to do is solve for this in order to be able to get that particular species. So we have a couple of options that we have to approach this. Again, the goal is to come up with a strategy for yourself. The first things first is just writing an equation and getting all our Ka values. Next, start figuring out how we can relate all this information to help us answer the question. Okay, so since we're dealing with polyprotic, we know we're only going to focus on Ka1. So that means I'm only going to focus on the first step reaction. So I have H2ASC plus water is going to give me H3O plus my conjugate base here. Now my initial amount that they gave me is 0.050 molar. We know water we can ignore. 0 for all of our products, and then we know our values for equilibrium are X and X for our products here. For our reactant, it's 0.050 molar minus X. Now our Ka value is times 10 to the negative 5, so we can effectively make an assumption here. So I say Ka1 is going to equal to X squared divided by 0.050 molar. This entire thing is equal to the Ka1 value, which is 1.0 times 10 to the negative 5. Of course, I'm going to effectively cross multiply here. When I cross multiply, I get 5 times 10 to the negative 7. To solve for X, I'm going to take the square root of both sides. I get X is equal to 7.1 times 10 to the negative 4. So now I've gotten my X value for my HASC minus, and I've gotten my X value for H3O plus. And so, since they wanted me to find the concentration of HASC minus, I would simply write my 7.1 times 10 to the negative 4 molar. Now, they also want me to get pH. So right here, I can take my H3O plus amount that I've also found and use the pH expression. pH is equal to negative log of my X value, which is going to be negative log of 7.1 times 10 to the negative 4. And therefore, my pH is equal to 3.15. Again, I was able to use the H3O plus from this overall expression to solve for my pH. Now, the final thing they want us to do, this is 3.15, is get the ASC2 minus concentration at equilibrium. And the only way to do that is to use our Ka2 expression. Let's go ahead and get that written down. So we know we did not have to use our Ka2 value for our rice table. But now that it wants us to figure out the concentration of a Ka2 species, ASC2 minus, then guess what? I have to use my Ka2 expression. So Ka2 is equal to my products divided by my reactants based on me mixing this base here with water. And so what I end up having is to basically plug and chug and substitute everything out that is given to me. So Ka2 is given as 5 times 10 to the negative 12. We solve for this HASC minus as 7.1 times 10 to the negative 4. We also solve for H3O plus, which is also 7.1 times 10 to the negative 4. We're going to rearrange this equation to solve for our ASC2 minus, and that's all we have to do here. So what I'm going to do is cross multiply, and then I'll divide to solve for that. So I'm simply going to cross multiply here, and then I'll divide by H3O plus. So my ASC2 minus equilibrium concentration is equal to my Ka2 times HASC minus divided by H3O plus. Therefore, this is what I end up getting. We already know this is going to be 5 times 10 to the negative 12. And we know both of these is 7.1 times 10 to the negative 4. Okay? This is also 7.1 times 10 to the negative 4. So what can I do? I can simply just reduce this. And so the concentration I have for ASC2 minus is going to be 5 times 10 to the negative 12. We can actually keep that because we do have significant figures that are going to be one significant figure here. And so we could just use one from what's given. And for our rice table, just to reiterate, we did use an assumption based on 10 to the negative 5, but I could have effectively just took my initial amount here and divided it by my Ka1. And if it is larger than 400, I could have took my assumption based off of that as well, because it is larger than 400. Okay, folks, let's move on to the next subject,